All right. Okay. Good morning, or good afternoon, or good evening, depending on when you're watching this video. So this is going to be the lecture video for Friday, March 19th, 2021. So we are March 19, 2021. So as mentioned in the last lecture, this is an asynchronous lecture video. So this will be um, a non-live lecture. If at any point you have a question about something I've said or about the material that we're covering, please pause the video, mark down, the time and the message that I was trying to communicate, and send me an email and let me know where the confusion was, and I will address that as soon as possible. All right, so we are currently working through lecture set 5. As a reminder, we started lecture set 5 on Wednesday. And what we are talking about in lecture set 5 is cluster sampling. So cluster sampling is the fourth sampling scheme that we have studied in this course. The idea here is that we are collecting information from a group of observations rather than from individual observations. The motivation for the cluster sampling approach is that in some situations, the sampling frame for all individual elements in the population could be very complicated. And on top of that, trying to connect or collect information from all of those different individual elements could be very time consuming and costly. Stratification was an approach to help us reduce the cost associated with collecting information from each of the elements, but stratification did not help us reduce the complexity of the frame. Cluster sampling would provide a solution to both issues. So it would reduce the cost associated with collecting information, and it would also reduce frame complexity, because instead of sampling each individual unit, we would be sampling collections of units from the population of interest. Okay, so on slide 8, we have the estimators for the average and the total for the cluster sampling scheme. Noticeably here, in both the total, or the estimate for the total, and the estimate for the variance of the mean, so equation 1 variance estimate here and equation 2 total estimate here, we have capital M. Capital M is the total number of elements across the entire population. So this was what we traditionally called capital N, but we now call capital M in the cluster sampling scheme, because capital N represents the number of clusters in the population. If we do not have capital M, we can estimate it using M bar. Alternatively, if we do not have capital M, when it comes to estimating the total, we can use the approach given in equation number 3, which you can see does not depend on M at all. So we worked through 2 examples. The first example, we discussed the estimation of the population mean based off of cluster sampling, and then we bounded that in the normal way using the estimate of the variance of our estimator for the mean. And then in example 2, we computed our estimates for the total and the variance of the total. And of course, if we wanted to, we could take this bound and bound our estimate. Okay, so today, what we're going to do is talk about the comparison between the cluster sampling estimates and the simple random sampling estimates. So we're going to show how, through a special case of cluster sampling, we can derive an estimate for the variance of simple random sampling and use that to compute the relative efficiency of the cluster sampling approach to the simple random sampling approach. Following that, we will talk about sample size calculations for cluster sampling. In this particular case, we will focus on calculations to compute the number of clusters for the cluster sampling scheme. And then following that, we will, if time permits, talk about proportion estimation. I mean, traditionally, I sort of set out with a larger list of goals than I'm actually able to get to, but we'll just see how this goes. Okay, so the first topic, the comparison of our cluster sampling approach to our simple random sampling approach. Now, we have already talked about the strategical benefits of using cluster sampling compared to simple random sampling. So we know that cluster sampling is a technique that allows us to reduce frame complexity, and it also allows us to reduce cost associated with collecting information. But we have also established that cluster sampling is effectively just simple random sampling where you're changing the definition of the units. So what if we wanted to compare the two approaches? So if we were in a situation where we wanted to know if for whatever reason cost and complexity of the frames were going to be fairly similar, which approach is better? We have defined the better sampling approach as being the one that results in the smallest variance. So inevitably, the goal of this comparison will be to define a relative efficiency comparison between the cluster sampling approach and the simple random sampling approach. Now, one of the things that we have to take into consideration when we are defining this relative efficiency approach, we know that relative efficiency measures work best when they are applied to the same sample. So in our previous illustrations of the relative efficiency, we compared, for example, ratio estimation to simple random sampling, ratio estimation to regression estimation, ratio estimation to difference estimation, regression estimation to difference estimation, etc. And in all of these cases, we use the same sample of data to make the comparisons. With the cluster sampling scheme, if we want to compare the relative efficiency of this cluster sample to the simple random sample, it's not as clear how we would do that for the same sample because of the construction. Okay, so we're going to get at this comparison through effectively a decomposition of the total variance in the cluster sample. So we're going to use our understanding of the ANOVA procedure to arrive at an estimate for the simple random sampling variance based off of a cluster sample. Just because this is showing up, there's nothing wrong here. This is just like a treatment for cracked skin. Okay, so we're going to start off by considering a special case where all of the cluster sizes across the population are equal. So just as a reminder, so little mn here, this is the size of cluster n, right? And then this would be like size of cluster 2, etc. So we're going to consider the special case where these are all equal. So we have a bit of a limitation in that sense, but this is what we're going to work with to try and build our comparison. All right, under this condition, the estimators given in equation 1 are unbiased, and then the estimators given for mu and tau in equations 2 and 3 are also unbiased. Okay, so the estimators that we've looked at so far in the cluster sampling scheme are unbiased when the population or the number of elements in each of the different clusters are equivalent. All right, so given that that is the case, another result is that we can now estimate the population mean using what's given in 4. So you can see here what I've designated as mu double tilde C. This is the double sum across the number of clusters and the number of observations in each cluster of Yij divided by 1 over m minus n. All right, and again, we're able to do this because cluster size is equivalent, because this would be the same thing as 1 over little n multiplied by the sum from I equals 1 to n of 1 over mi yi, but since each mi is equal, that becomes a constant and we can pull it out. Okay, so that is the idea here. Sorry, and I'm just missing this one part in front, which is the sum from I equals 1 to little m. These are j's. All right. Okay, now the variance for our estimator of the population mean in the situation where the cluster sizes are equivalent is given in equation 5. So you can see we have our SPC, we have 1 over n times m squared, we have 1 over n minus 1, which would be the traditional denominator for the variance term. And then we just have the sum of the yi minus mu t, which we defined on the previous slide to be the mean of, well, the average for each of the different clusters over little n. Okay, so the total for each cluster over little n. Oh, and I actually have that right there too. Okay, so all other values are as previously defined. So the yij is the jth observation for the i's cluster. And like I just said here, mu hat t is the sum of the yi in each cluster, or the sum of the yi across the clusters over n, okay, which is equivalent to m times mu double hat c. Okay. All right, so let mu hat I be the sample average for cluster I. Okay. So mu hat I is equal to yi over m. So m is the size of each cluster. Yi again is the value of the response for the cluster. So the average for that cluster is going to be yi over m. This means that the yi is equal to m times mu hat I. Okay. From this, we can make the following declarations. 1 over m squared times n divided by n minus 1 multiplied by the squared deviations of the yi about their mean is equal to 1 over m squared over little n times n minus 1 multiplied by the sum of the squared deviations between m, so the cluster size, multiplied by mu hat I minus m times mu hat c, which again is the average or the estimate of the population mean across all clusters. All right, so it follows that we can pull the m's out from this expression. And in that case, what we can show is that this reduces to 1 over n times n minus 1 times the sum of the squared deviations of the cluster average about the overall average squared. Okay, and that's what's in equation 6. All right, so using what's in equation 6, or starting from the definitions given above, we can show that if we consider the double sum of across all clusters and across all observations within each cluster, so now I'm here, okay, of the yij minus the cluster, the average of the population mean squared, right? So this quantity here is total squared deviation, or sorry, let's say total squared difference between each observation and the overall mean, right? So this first term here, the total square deviation between each observation, so the individual element and the overall mean, this would be a representation of the total square difference in the entire population. So if we were to take this quantity and divide it by 1 over m times n, that would be the total variance for the entire study, or an estimate of the total variance for the entire study. Okay, so we're setting up a complete decomposition of the sum of squares, right? So this thing here is also effectively our SST from our traditional ANOVA studies. Okay, we can show that this is decomposed as is described in equation 7, right? So we can take this and we can basically break it up into two terms. We have each element minus the mean of its representative cluster. So this would basically just be your SSW, or your SS within, or your SS error, if you think of it as in an ANOVA, a traditional one-way ANOVA sense. And then this term here, this is going to be your squared deviation between each of the clusters. Okay, and we can show that since neither of these values actually depend on m, this thing can become the same SSW term plus m times the sum from I equals 1 to n. Okay, so we have SST SSW, SSB. So we're taking complete deviation of the entire study and we're breaking it up into two components. And these are effectively the exact same things that we would see in a one-way ANOVA. All right, so from those formula given in 7, so that decomposition of the sum of squares, which is, again, the classical, and when I say classical ANOVA, I mean one-way ANOVA. We can write that the mean squared between, so the variance of each individual group is simply that SSB term over n minus 1. So that's going to be, or sorry, this is the difference between the means of each of the clusters. Okay, so that's just going to be m over n minus 1, so the number of clusters minus 1, times the sum from I equals 1 to n of mu I hat minus mu hat c, mu double hat c squared, right? So that makes sense. This is our estimate of the variation between the clusters. MSW is going to be the estimate of the variation within each of the clusters. So you can see from the definition shown in equation 9 that we're taking square difference of each observation, so each element in the study, and subtracting the mean of that cluster, right? So these are very traditional estimates. And then we can say that the variance of mu double tilde c, so of our estimator, is going to be the FPC multiplied by 1 over n minus m times the MSB, okay? Now, this part here also makes sense because if we go back and we look at the form of the estimator shown here, you can see that, well, this is for the total rate, so mu tilde. Can we see it from this? It would be great if we could. No, sorry, you can't really see it from those, even though I'd hope we would be able to. But we can say that based off of this ANOVA approach, the estimate for the variance of the cluster sampling mean is going to be given by 1 over n minus n over 1 over n minus the FPC times 1 over n times n times m times the MSB, okay? I was hoping we'd be able to see it more directly from what we had given before, but it's not completely clear how that the term in 8 relates directly to those terms before. Well, I think actually the other thing that we would need, shouldn't waste too much time with this. So we have yi is m over mu I. Oh, actually that's, yeah, so you can see it from here. So if you go back and you look at what was shown for the total here, so compare this to slide 12/13. So here we have yi minus mu hat t. And then here we have yi is m mu I. So that's yi mu I here, the m mu c. And then if we make the substitutions down here, it should be a little bit more clear how we're getting to that estimate. So we pull the mi out. We would still be able to do that. Yeah. So it's not completely clear, the relationship, so you can't see it like directly when you compare it to the previous formula, but if you follow the path of how we substitute y equals to m mu hat in equation number 6 and then use that in SSB down here, you can kind of see more clearly why we arrive at the estimate given in 10. But I admit that it isn't as clear as I would have liked it to be. Okay. Okay, so if we had taken n times m observations in a simple random sample and used those n times m observations to compute mu hat and sigma hat squared, then our estimate for the variance of mu tilde is going to be 1 minus n times m over capital N times m of sigma hat squared over n times m, right? So this should be fairly logical to you because you're basically just saying that we have n times m total observations in the sample that we have collected. So then we would have capital N times m total elements in the population. And again, the reason we can say this is because we are assuming that m is consistent across all samples, right? So since, actually that would be in the lower part here. So since m is equal across all clusters, right? So if we wanted to compute the relative efficiency of mu double tilde C to mu tilde, which is our SRS estimate, what we can do is compare the MSB from our declarations given above to sigma hat squared, which again, this is the SRS estimate. But we're not going to be able to calculate sigma squared directly, so we can approximate it using what's given in equation 12. So we write that sigma hat squared can be approximated by sigma double hat squared, which is approximately 1 over m, so number of elements, times m minus 1, multiplied by the MSW plus the MSB. Okay. All right, so let's look at an illustration of these ideas. So we have an inspector wants to estimate the average weight of fill for cereal boxes packaged in a certain factory. The cereal is available to him in cartons containing 12 boxes each. See the table below. All right, so we have 5 cartons. We have 12 boxes per carton, and we have the little m, the little yi for each of the different cartons. So that's going to be our variable of interest. Right, so these are going to be the clusters, right? These parts here are going to be elements per cluster. So those are the m. So we have m is equal to 12, right? So this gives us little n is equal to 5. And then we have the yi, which again are the response variable. Okay. I think that is actually. Okay, so in part A, we want to estimate the average weight of fill for boxes packaged by this company. So we just want to estimate the average. In part B, we're going to use the ANOVA table given on slide 16 to place a bound on the error of estimation. Assume n is large enough to ignore SPC. Okay, so here's our ANOVA table. And we want to utilize this to bound our error, our estimate for the mean. And then in part C, we want to compute the relative efficiency of mu double tilde C to mu tilde. All right, so starting in part A. Okay, so first note M1 equals M2 equals M5. Okay, so we have consistent cluster size across each of the different clusters. All right, so since we have consistent cluster size, right, so therefore we can use mu double hat C, which is 1 over little m times m of the sum from I equals 1 to n times the sum from j equals 1 to m of the yij. Okay, so in our particular study, this is going to be 1 over 5 times 12 multiplied by the sum from I equals 1 to n of each of the different yi's. So the yi's are already the total, right? So this is actually the sum from j equals 1 to 12 of yij. So this is basically just going to be the sum from I equals 1 to n of the yi as they are written in our illustration, right? So, I mean, just for clarity too, if you're a little confused about that, like we already have the sum across the observation. So if we wanted to use this formula directly, the yij would be each of the values that are inside the table here, right? So like y11 would be 16.1, y12 would be 15.9, y21 would be 15.9, y31 would be 16.2, etc. But we already have the sum, so we can simplify this, and that gives us 1 over 5 times 12 of 960.3. Okay, so that's the sum of these values here. Okay. And that gives us 16.005. All right, so in part B, we want to bound this thing. And then in part C, we want to compute the efficiency. Okay, so let's talk a little bit about bounding it. So in order to bound it, we're going to need to get our MSB term. So maybe I'll just make a note here. So or actually, let's just look at it like this. So the bound is equal to 1.96 multiplied by the square root of the variance of mu double tilde c. So that's going to be 1.96 multiplied by the square root. And then we're going to have 1 over n times m of the MSB. Okay. And that's from equation 10. All right, so the purpose of the ANOVA table and filling out said ANOVA table is to help us find this estimate of the MSB. So you can see that here we have a traditional ANOVA table, but we don't have the F value because we're not looking for significant difference between the cluster averages in this case, though we could do that actually. But what we want to do here is just work out the values for the table. So first off, the table is going to be based off of what we have observed in the sample. So the factor degree of freedom is going to be the number of clusters minus 1. Okay, so DFF is going to be little n minus 1. So this is 4 because we have 5 clusters in total. So 5 minus 1 is 4. And then the next thing that we would do is compute the DF total. So the DF total, and then actually I should also know that this is going to be the between, this is going to be the within. So the DF total is going to be n times m minus 1. So we have 5 times 12, which is 60. 60 minus 1 is 59. And then this is going to be the difference, right? So the DF error in this case is going to be the difference between the two, which would be n minus n, which would be n times m minus 1 in this case. 11 times 5 is 55, so that works out. All right, now we can approach this problem in a couple of ways. Since we have the sum of square total and we have the mean square factor or the mean square between, we can actually just use those values to work out the remaining values in the table. So this would be done simply by saying, for example, SSF is going to be MSF over DFF. So through that relationship, we can easily work out the sum of square for the factor, or sorry, this is, so through this relationship, so MSF, we can easily work out the sum of square for the factor. We also know that SSF plus SSE is equal to SST. So through that relationship, once we have the SSF, the SSF, we can get the SSE. And then it's also worth pointing out that the MSE is going to be the SSE over the DFE. Okay, so standard ANOVA formula that we can utilize to calculate our values. Now, we can do that to confirm it, but I also just want to show quickly how this would work if we had to do it by hand so that you have that idea. So if we wanted to compute the SS factor, this is going to be the sum from I equals 1 to n of the mu hat I minus the mu hat C. So this is going to be little m times mu hat I minus mu hat double C squared, right? So this would be 12 times, and then for example, we would have our first cluster average, which is 192.1 over 12 minus 16.005. Okay, and then this thing would be squared. And then we would do this for all the calculations. So then we would end up with the fifth one, which is 191.3 minus 16.005. That would be squared, right? Okay, so our SSF calculation can be found by exploiting the rules in the ANOVA table, but it's also just the squared deviations between the cluster average and the overall average. So it can also be found just by taking the averages of the 5 clusters in our sample and subtracting 16.05. All right, so the SS error is going to be found by taking the sum from I equals 1 to n and the sum from j equals 1 to little m of each yij minus mu hat I for each of the different clusters. Okay. And then this one is basically going to take each of the values from the actual cluster sample and then subtract off the mean. So this is a much more difficult illustration because the values change so often in the calculation. But for example, for the very first value, so if we used cluster 1, we would have 16.1 minus 191.1 over 12 all squared, right? And then you would keep moving along this cluster. So then you would have, for example, 15.9 minus 191.1 over 12 all squared. And then you have to do that for every single value in each of the clusters across each of the different rows. Okay, so with that being said, we can use these ideas to verify the values. Now, in order to get the SSF, we just take our DF and we multiply it by the MS for the factor level. So that's going to give us 0.0276. Okay, and then we can take 1.3085 and subtract 0.0276. That's going to give us 1.28083. And then we would take 1.28083 and divide by 55. So if we do that, just wanted to confirm, we will get 0.02328782. All right, now we can bound our estimates. Right. right? So the variance of mu tilde c hat is equal to 1 over nm times msb, which is equal to 1 over 5 times 12 times 0.0069. Right, and that gives us 0.000111527. Just gonna make sure I have that right. Yep, okay. All right, and now the bound is just going to be, so the bound will be 1.96 multiplied by the square root of 0.000111527, which is equal to 0.021. Right? And then we can use that to bound our average. Okay, now the last thing that we wanted to do here was part C. So in part C, we want to compute the relative efficiency of our cluster sample to our the simple random sampling scheme. Right, so that means that we're going to compare the MSB to the spacing issues, right? I think maybe I can fit this on the next slide. But so we're going to have here relative efficiency of mu double tilde C over mu tilde Y. So that's our SRS estimator. So this is going to be the variance of mu double tilde C over the variance of mu tilde Y. Okay. Okay, so I'll just say see next slide here. All right, now from before, okay, so relative efficiency. Okay, so from before, we know that if we wanted to compare these, we can compare the MSB to sigma hat squared directly. So we have MSB to sigma double tilde. We'll call this Y. Okay, so our MSB was the mean square between, so that's 0.0069167. All right, and now we're going to divide by sigma tilde Y. Now this is approximated by 1 over M multiplied by M minus 1 times the MS within plus the MSB. So this gives us 0.0069167 multiplied by 1 over 5 multiplied by, or sorry, 1 over 12 multiplied by 12 minus 1 times 0.023288787 plus what we have above. Okay. All right, and then I just need to check this one real quick here. So we're going to have 1 over 12 times 11 times 2, 1. Okay, and then that gives us 0.315. Okay. Oh, sorry. Damn, I inversed this. Okay, sorry, 1 sec. I'll fix it after. This should be inversed though. I flipped the expressions. There we go, 3.17. Yeah, that makes sense. All right, so the conclusion will be the same. So this shows, I really gotta like patch this up after, but so this shows that the cluster sample is more efficient. Okay, and I'll clean the slide up afterwards. And so it's the same result. I accidentally put MSB in the numerator. It should be in the denominator, so it should be 1 over 0.315, but it gives you the same conclusion. But technically, this is the relative efficiency of mu y to mu double hat c, not mu double hat c to mu y, because I have these flipped. So these should be turned around. But again, I'll fix that part after. All right, so with the remaining time, we'll just talk a little bit about sample size calculation. So this is, we're now on slide 17 here. So we have in cluster sampling, there are 2 factors that affect how much information is collected: the number of clusters and the relative cluster size. So we're going to assume cluster size has been chosen to minimize the variance of the estimators as much as possible. Therefore, we are concerned with, right now we're concerned with calculating the number of clusters, little n. So we're going to focus on the calculation of the number of clusters to be sampled. Okay, so if we are utilizing cluster sampling to estimate little mu, we have the following. So we have B is equal to 1.96 multiplied by the sum from 1 over little n times capital N of sigma hat squared C divided by n times m bar squared. Okay. Now in this case, if m is unknown, let little m bar, or rather use little m bar is equal to the sum from I equals 1 to n of the mi divided by n. All right, so from this will work out with the example actually. Okay, so from this, we can show that a little bit of rearrangement gives us kind of a traditional estimate. So we have n is equal to b squared multiplied by m bar squared divided by 1.96 squared times sigma hat squared c plus 1 over n inverse. Okay, so now let's take this idea and illustrate a calculation for the number of clusters. So we have considered the data given in our original illustration. Suppose that the manufacturer determined that a total of 710 bandsaws were sold to industry. Okay, so this means here that we have that we have the sum from I equals 1 to capital N of the MI is equal to 710. We had N is equal to 96, and we had sigma hat C is equal to 845.5607. Right, so these two values here are from the original illustration. Example 1. All right, now we can estimate M bar. So M bar is equal to the sum from I equals 1 to N of MI over N. So this is 710 over 96, which is equal to 7.395. Sorry, 7.396. All right, so that means that our sample size for this problem, so the researcher determined that 710 bandsaws were sold to industry. How many clusters should he select for the sample if he wants the bound on the error to be less than $2? So we have 2 squared multiplied by 7.396 squared divided by 1.96 squared multiplied by 845.5607 plus 1 over 96 to the negative 1. So this gives us roughly 12.858. Therefore, n equals 13 clusters should be selected. All right. Okay, so I have one more illustration of a sample size calculation to work through. But I think what I'll do is I'll stop here for today. Again, I'll clean up the slides a bit, and then on Monday, we can revisit the sample size calculation example, and we can look at another example to kind of go over those steps again in a different scenario, and then we can move on to proportion estimation. All right, so as I mentioned before, this was an asynchronous lecture for Friday, March 19th. If you have any questions about the material that was covered in today's lecture, please let me know. I'm more than happy to try and help with that. And otherwise, the reminders that we gave at the start of class on Wednesday, March 17th, those are still the same. So we have a lab quiz on the 29th of March, which is a Monday. Let me know if you need accommodation for the quiz sooner rather than later. I'll post the exact lecture slides that are going to be covered, and I'll get some practice problems up for that as well. And we have an assignment due on April 9th, which is the 4th assignment, which is ready for you to start working on. And that covers ratio estimation and stratification and the cluster sampling material from lecture set 5. All right, so have a good weekend, and I will talk to you on Monday.